Hello, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinars. And I thank Dr. Curtis Larson and the NASA Engineering and Safety Center for making this series of webinars possible. Our topic today is rectangular plate shock and vibration. So this unit will present plate bending, shock and vibration, and the plates will be modeled as continuous systems. So that's where we start with a governing partial differential equation and find solutions, closed form type solutions. And another common way of modeling plate bending is the finite element method. And we're actually going to cover finite element analysis in a future webinar unit. Now, when we talk about plates, these rectangular plates, they could represent a circuit board. And what we do is we take the piece part mass, or rather the total mass of the circuit board, including its piece part mass, and we smear that uniformly across the board. That's a simplifying assumption that we normally make. So we're going to do a normal modes analysis, and then we're going to take these plates and subject them to base excitation, which, given that it's a continuous system, is more properly referred to as enforced acceleration. And we're also going to take a look at Hund's stress-velocity relationship for plates. A couple of references here. The one that you should really start with is Arthur W. Lisa, and this is NASA SP160, vibration of plates. And Lisa goes through plates for rectangular geometry as well as circular plates, annular plates, elliptical plates, for a whole, all the different permutations of boundary conditions. And he gives the equations for the natural frequencies and the mode shapes. And all these references are available via links on my blog for this webinar unit. Also, Steinberg vibration analysis for electronic components. Steinberg takes Lisa's formulas and simplifies them and just covers the natural frequency equations for common rectangular plate boundary conditions in a couple of pages in his reference book. And that there's some additional papers posted at the Vibration Data blog as well. So here we have Hund's plate bending stress velocity for simply supported plates. And Hunt wrote in his 1960 paper, it is relatively more difficult to establish general relationships between antinodal velocity and extensional strain for a thin plate vibrating transversely, owing to the more complex boundary conditions and the Poisson coupling between the principal stresses. But he did come up with a formula for higher modes for what he refers to as intermodal segments. So imagine just a kind of a small rectangular patch here where we have the length along the y-axis, the length along the x-axis, and he came up with a stress-velocity relationship for this patch. Now these dashed lines here are the nodal lines, and the nodal lines are the lines at which no translation takes place. And the equation I'm about to show you, I've verified that it works just for the fundamental mode of a simply supported plate. But for other boundary conditions, it does not seem to work out very well for fundamental modes. Now, maybe by the time we get to higher modes, regardless of what the peripheral boundary conditions are, his equation will work for the higher modes, because these nodal lines for the higher modes tend to be accompanied by a behavior where the little patch is almost like it was a small, simply supported rectangular plate. So here's Hund's plate bending stress velocity relationship for simply supported plates. So the intermodal stress, and then we have sigma sub int for interior and comma max for the maximum. And then he has two formulas here for the stress in the x-axis and the y-axis. And rho is the mass density, c is the speed of sound in the material, And then this is the Poisson ratio. And V sub int comma max is the intermodal particle velocity, the maximum velocity. Then once these two stress components are calculated, they can be combined into a von Mises type stress relationship. One other thing I wanted to mention is in terms of these intermodal stresses, for a white noise base input, typically about 90% of the stress in a rectangular plate is going to be due to the behavior or response of the fundamental mode, which is the first mode. And as we include a higher number of modes in our analysis, there's a real diminishing returns as to how they affect the total bending stress. So just sort of keep that in mind. And there needs to be some work done for developing stress-velocity relationship for other boundary cases, for the fundamental mode in particular. And that's sort of a work in progress that I'm doing on the side right now. So let's go to our vibration data GUI package, and I've got another, well, it's actually a new feature to show you this week. So I'm going to the Matlab workspace to vibration data, and this week we're up to version 6.4 and rising. And what I've done is, well, let's go to import data to Matlab here. And this read data, we've actually used it before, but I've modified it a bit. So we have three options for reading data into the Matlab workspace. We can read in an external ASCII text file, and we've actually done that before. We can load a star.mat file. And the new feature for today is I have some library arrays, and these are arrays we've used in the past, and we occasionally reuse them in ongoing and future exercises. So the navmat spec, we've used that before. Let's go ahead and just read in this array. And by the way, the four arrays you see listed there, those are now distributed in the vibration data zip file. So if you get the latest version of vibration data, download it, extract the files, you will get these data files. So let's read in the navmat spec because we're going to use that today. So we've just read it in, and it's going to be navmat_spec. The units are frequency in hertz and g² per hertz. So if you look over to our Matlab workspace, you can see that that array is now available. Then we're also going to use this synthesized time history to satisfy the SRS spec with the 1000G plateau, and we've used this one before. So let's read in that array. So that's SRS 1000G _ XL with units time in seconds and acceleration in G. So we now have both of those arrays in our Matlab workspace, and we're going to be using each of those two arrays as base input for, we're going to do two different plate cases with different boundary conditions. Okay, so let's start with a simply supported plate. This will be aluminum, and it's simply supported about all four edges. Its dimensions are 16 by 12 by 1/8 of an inch. So we're going to have English units, aluminum, elastic modulus, and Poisson ratio are just available since this is a library material. And let's actually just go to this GUI within our workspace. We'll come back to the PowerPoint slide in maybe about 10 or 15 minutes or so. So let's go to structural dynamics. This is the main GUI page for vibration data. And we're going to do plates, rectangular and circular. And we have an option here, rectangular plate, simply supported about all edges. So this program calculates the bending frequency of a plate simply supported along each side. English units, aluminum, just double check the elastic modulus and Poisson's ratio. The mass density for bare aluminum. Now we have an option here. We could add some non-structural mass. And in this case, we're not going to do that, but if we did, that would be uniformly distributed over the surface area. And the dimensions are 16 by 12 by 1/8 of an inch. So we're going to return now. No, we're not going to return now. We're going to calculate natural frequencies. So we're going to take a look at the first 4 mode shapes. This is you could call this the bending modes. So the fundamental bending mode, 128 Hertz, all points in phase, same phase angle, all the points across the surface area of that plate. And this is the mode that's going to typically, for a white noise input, is going to cause typically about 90% or so of the bending stress. And the peak bending stress is going to happen right at the center. So that's the first mode. Now the second and third modes, maybe we should look at them together. Each of these 2 modes has a nodal line. So in one case, the nodal line is parallel to the width, and in this case it's parallel to the length. And the nodal line is the line at which there's no translation occurring, but there is rotation at the nodal line. And something interesting about each of these 2 modes is that the 2 halves are vibrating 180 degrees out of phase with one another. So there's an equal amount of mass going up as there is going down. And that's true for each of these 2 modes, the second and third. Well, as a consequence of that, if we have a uniform and forced acceleration about the periphery here, the perimeter, neither of those modes can be excited. In other words, the participation factor of each of those 2 modes is 0. If we had some reason to excite those and we were applying a base excitation or enforced motion, we would have to have a differing phase angle, or we would have to have a differing amplitude or both along the perimeter. But for a uniform constant amplitude in phase base input along the perimeter, neither of those 2 modes can be excited. The fourth mode here can be excited. It's in this case nearly 500 Hertz, and you can see that there are 2 nodal lines. So for this case here, we've got the 2 nodal lines as shown. And if we had the time and inclination, we could look at higher modes as well. But currently, this software is just set up to display the first 4 modes. I guess if someone has a need to look at higher modes, they can send me an email, and I'll maybe modify that program. So we also see this text output here in the Matlab command window. And you can see the fundamental mode, and the M and N refer to the nodal lines. And the number of interior nodal lines is equal to M-1 and N-1 for the respective modes. So M and N are referred to maybe more properly as indices. PF is a participation factor. Then EMM, this is the effective modal mass in terms of a ratio. So the first mode, the fundamental, has the highest participation factor. It also has the highest effective modal mass ratio. So with the white noise input, this is the one that's going to be most excited. So most of the response will be due to the fundamental mode. But several of the higher modes also have non-zero participation factors, and you can just kind of take a quick look at that right there. Okay, so let's see what we have next. So the next thing we're going to do is we're going to apply base excitation. And just for simplicity, we're going to do a Q is equal to 10 for all modes. So if we wanted to, we could instead input the equivalent viscous damping ratio, which would be 5% for the case of Q is equal to 10. We also have the option to vary the damping by mode. Let's go ahead and save the damping. And we might want to take a quick look back at the command window here, because this gives a listing of the first 16 modes, and going forward in the base excitation, we're going to include 16 modes, corresponding natural frequencies, corresponding Q values, corresponding damping ratios. So you can see we've successfully specified Q is equal to 10 as a uniform amplification factor for all modes. And again, if we had a reason, we could actually vary that by mode. Let's take a look at the transmissibility. This is the transmissibility for base excitation for our simply supported plate. So we're going to take a look at the center location, and let's just put from say 10 to 10,000 hertz for our frequency limits for our transmissibility plots. Calculate, and a bunch of plots come up, and so here's our relative displacement frequency response function, and this is at the center of that plate because the plate is 16-inch long and 12-inch wide. So the 0 point, the origin, is at one of the corners. So we have the relative displacement in inches divided by the base acceleration g. And we see the fundamental mode here at 128 hertz. And then there's kind of a steep roll-off here. And you do see some of the higher modes kind of having their little peaks there. But clearly, for the case of a white noise input, the relative displacement response would be dominated by the fundamental mode. In fact, almost exclusively due to the fundamental mode. If you look at this mode here, let's see what this mode is. That's at 772 hertz, or thereabouts. So that looks like it's actually corresponding to the 7th mode. Now, the second and third modes are both zero participation factors, so they don't even show up. But the 4th mode did have a non-zero participation factor near 500 hertz, but you can't really see that at all. But if we go to a different location on that plate, so let's do a quarter length, quarter width, let's see how the transmissibility changes there. So if we go to the quarter length and quarter width, we do see the 493 mode appearing, and it's listed nominally as 496.7, but due to the effect of damping, there's a slight decrease in the actual modal frequency. And actually, I want to go back to the center location. That was just a little side trip there, and I think what I'll do is a close all, just because I get too many plots up there. Okay, let's go to the let's go back to the centers real quick to rerun anyways. And so here's the von Mises stress. This is the transmissibility for the center location of the simply supported plate. So we have the transmissibility, the PSI, that's the stress, divided by G. And you can see the modal peak here, spectral peak at 128 hertz. And then at the second location, you can see also the effect of this higher mode here. So still, for white noise input, most of the stress is going to be due to the fundamental mode. But if we want to include some higher modes, that they will also contribute to the overall stress. Here we see the shear stress, which this is actually, the shear stress at the center of the plate is actually zero, theoretically, but there's some kind of noise going on there, numerical noise, so we can just disregard that. The two bending stress components for SXX and SYY, and those two components get fed into the von Mises stress calculation. Okay, here's the acceleration power transmissibility at the center of the plate. This is actually G square out divided by G square in versus frequency in hertz. The 128 hertz spectral peak for the fundamental mode is very prominent. And this higher mode here is also contributing to the overall response. And this will become particularly important, these higher modes, when we do a pyrotechnic simulation, a base input. And here's the same frequency response function for acceleration, except in this case it's just going to be g out over g in. So response acceleration divided by base acceleration. And here's the relative velocity, inches per second, divided by the base acceleration in g. So for relative velocity, or sometimes we kind of wave our hand a little bit and call this pseudo velocity. You can see the pseudo velocity is dominated by the fundamental mode. And then the relative displacement, which we've seen before. So those are just the transmissibility functions, and if we had need, we could export those to the Matlab workplace. But let's go next and just have some fun, and let's do a NavMat PSD base input to this plate simply supported about all edges. So the input array must have two columns, frequency in hertz, acceleration g squared per hertz. And we do have the NavMat spec, because the first thing we did in Matlab today was we read in two of the library arrays, and one of those was the NavMat spec. So this is already in our Matlab workspace. So we're going to do the center of the plate, and let's see what the PSD response is at the center of the plate. Okay, going to take a few seconds there to get through. Okay, so here is the von Mises stress PSD at the center of the plate. So psi squared divided by hertz, that's a stress PSD versus frequency in hertz. And the overall response is 443 psi RMS. Then we also have our relative displacement PSD, inches squared per hertz, relative displacement versus frequency in hertz. We've got a relative velocity PSD, inches per second squared per hertz versus frequency in hertz. And we have our acceleration response PSD. Maybe I need to kind of arrange these in some sort of order that makes sense. So here we have g squared per hertz versus frequency in hertz. The blue line is our NavMat base input, and the green line is the response at the center. So the fundamental mode response is very strong there. But this higher mode is also contributing to the overall response energy, and to a lesser extent this mode that is yet at a higher frequency, natural frequency. So anytime we take a plate and we apply a uniform in-phase base excitation along the perimeter, we can get some really high responses at the center of that plate, or at other locations depending on the boundary conditions. Now as we go from acceleration to relative velocity, we can see, as is the case in all these plots, the response at the fundamental mode is the dominant effect. And for the case of relative velocity, this higher mode shows up a little bit here, but not nearly as much in a relative sense as it did with acceleration. And then by the time we get to the relative displacement, we can almost say that the response is almost exclusively due to the fundamental mode, and these higher modes just don't make any difference. And then as we get to go to our stress PSD, well, it kind of sort of looks like the relative velocity PSD in a hand-waving sort of way. But it's its own it has its own unique character as well. Now another thing that we can do here is we can go to our command window, and we can see what the responses are for the various metrics in terms of the overall levels. So the acceleration response, almost 17 GRMS. Relative velocity, that's round up to 7 inches per second RMS. Relative displacement response, rounded up to 9/1000 of an inch RMS. And the von Mises response is 443.4 psi RMS. Now, if we use our Hunt, our maximum global stress value from the stress-velocity relationship, that is very, very close to what the von Mises stress is. So in this case, those two values are in very good agreement with one another, and that's a good sign. And again, this is a special case of a simply supported plate. This Hunt maximum global stress relationship may not work so well for other boundary conditions, and I'm still kind of investigating that myself. So that's how to do a PSD response for that plate. And if we wanted to, we could save these other metrics. And I just remembered something that I wanted to show you. So let's go back to, if I can find it. Okay, I may have closed out the window. Let's do something here. Let's go to apply base excitation. We're just kind of doing a little backtracking here. Save the damping. Q equals 10 as before. Let's go back to transmissibility because I want to show you something here. Okay, 10 to 10,000 hertz. Yeah. So all those different curves flash by. We've seen them before. Let's save the absolute acceleration. I'm just going to save this as accel_trans, and you can call this anything you want, just as long as you remember what it is. So we're saving that, our output array. Now we're going to go back and do something that we haven't done in quite a bit. But we did it kind of early on in the webinar series. We are going to take a look at damping. Well, we already know that Q is equal to 10 for all the modes because we specified that. Well, let's sort of pretend we have measured data instead of analytically generated data. So let's go to damping functions, and we're going to do the half-power bandwidth curve fit. So we've actually run this before. This method performs a curve fit to determine the damping ratio for a system excited by base excitation or an applied force. This method is an extension of the half-power bandwidth method. The input data must be a frequency response function. Now, I've learned by experience it's very important to get all these boxes, these list boxes, checked correctly. So our frequency response function, it's a transmissibility function, accel_trans. It is base excitation. Let's just have the plot limits automatic for now. And let's do an acceleration response. And this is amplitude. It's G out over Gn. And let's just go ahead and plot that input function, which we've seen this before. Now, if you don't recognize it, it's because it's linear plot. And I don't actually have the y-axis unit here, but it is G out divided by G in. Then we have our frequency in hertz. So let's kind of zoom in a bit on that fundamental mode. So we're going to zoom in on the fundamental mode. Okay, this is the mode that we want to do the curve fit. Now, before, when we had a spring mass system, we learned that we could pick off the Q value from the peak. So if we take the peak, and this peak would correspond to resonant excitation. So if a spring mass system is subjected to a resonant excitation in response, then its peak value is the Q. Well, in this case, we have a Q value of equal to 10, but we don't have a spring mass system. We have a continuous plate. So that neat and tidy and simple rule, it doesn't work anymore. In this case, if we tried to pick off Q from the peak, we would think that Q is just slightly above 16. Well, that's not true. Q is equal to 10. So we're going to use our more robust generalized method for determining the Q value from the peak. And it's the half-power bandwidth method. So let's do our curve fit. And we're not going to take this whole spectrum here. We're just going to kind of zoom in a bit. We get a little more accurate if we zoom in a bit. So let's just say, well, maybe from 110 hertz will be our lower frequency for our curve fit, up to about 150 hertz maybe. So we're going to do 10,000 trials from 110 to 150 hertz. Let's do the curve fit, and let's back out what our Q value is. Okay, so already we have a pretty good fit here, but we'll just let it run out. Okay. Now in this case here, we have the green curve is our curve fit, and I'm calling the blue curve measured data. Well, that's not exactly true because it's analytical data. But just for pretend, let's pretend that that blue curve was from measured data. If I go over to here, the natural frequency is 129 hertz, rounded off. The damping ratio, let's just go ahead and round off numbers. It's about equivalent to 5%, and Q is approximately Q is equal to 10. So our synthesized curve fit using analytical functions matches our measured data close enough, and we get some good values there. So even though that peak is at 16, that's 16 G out divided by 16 G out divided by G in. Even though that's the peak at resonance, the Q value is still equal to 10, and we find that out by using the extension of the half-power bandwidth method via the curve fit. Now, if we looked at those higher modes, it gets a little more tricky to just isolate those higher modes, but ideally we could also do the half-power bandwidth method on the higher modes as well. And you can play around with that as a homework exercise. Of course, everything I'm doing here I'd like you to do as a homework exercise. And just another kind of caveat about damping is don't spend hours and hours trying to refine your damping estimate to the third significant digit. That is not time well spent. If we can get in with a couple percentage points of what the true damping is, we are satisfied. Okay, I think I've probably covered everything I wanted on the simply supported plate. Let's go back and kind of take a look at the PowerPoint slides. I'm going to do a close all here just to close out all those plots. So I think we're done with simply supported plate. So what we could have done if we were doing a circuit board analysis, this is what I would have done typically, is I'd have said, okay, the circuit board material is G10, and if I had selected G10, then the corresponding elastic modulus, Poisson's ratio, and mass density values would have come up. Since G10 is it's a fiberglass material, it's a library material, and it's typically the material used for circuit boards. And then we could have added a non-structural mass to represent the piece part mass, which is uniformly distributed across the boards for the purposes of our analysis. And then we would have needed to verify that the total mass value was correct. And of course, put in the dimensions here. Now in this case, instead of doing a circuit board model, we just did bare aluminum with these parameters as shown here. And I'm showing you this PowerPoint slide, so as you go back and do the homework exercises, you can remember all the parameters that we did. And then we took a look at the natural frequencies, the modal indices M and N, the participation factor, as well as the effective modal mass ratio. Then we had our fundamental mode at 128 hertz, all points moving in phase. And we added a Q value of 10 for uniform amplification factor or damping. We saved that. We took a look at the bending transmissibility. We took a look at the acceleration frequency response function at the center. We took a look at the von Mises stress. And we also did the half-power bandwidth method to verify that fundamental mode had a Q value of 10 And here's the PowerPoint slide, similar to what we just did, which I just did for the demonstration. Okay. Oh, and wait, there is one more thing. I forgot the shock. Okay. Let's go back and do one more thing for our simply supported plate. So I'm going to have to kind of get back in here and so simply support about all edges, and I'm just going to quickly put the same dimensions back in that we've been using before for our simply supported plate. 16 by 12 by 1/8 inch thick. Let's calculate the natural frequencies. The fundamental mode will be at 128 Hertz. I'm going to close all to just close out those figures, those mode shape figures. I'm going to have to, one more time, enter the damping. Q is equal to 10 for all modes. Now let's go to arbitrary input. And this is where we can input a shock pulse. And let's go ahead and do all 16 modes. And our input is going to be a synthesized time history that we've worked with before, and it's SRS 1000G _ Excel. So SRS 1000G _ Excel at the center. All 16 modes included. So let's apply this shock pulse. And this shock pulse, with a little bit of imagination, could represent a pyrotechnic pulse. Now, if you've been following along in the webinar series, you've seen this pulse before. This is our base input acceleration. And we have acceleration g, and time is equal to seconds. And I see that I put the coordinates for the center of the plate, but this base input acceleration is actually what the perimeter of the plate is going to be doing in terms of the base input or enforced acceleration. So with some imagination, that's a pyrotechnic shock pulse. So at the center of the plate, we get the response acceleration for all 16 modes. We have a whole bunch of other plots here. We have a relative velocity plot. So you can see that the higher modes play a stronger role, or more prominent role, in the acceleration response than they do in the relative velocity response. Okay, we've got a stress component. Let's kind of skip over SXX and SYY, because we're more interested in what the von Mises stress is anyways. And then by the time we get to the relative displacement in inches versus time, you can see the relative displacement at the center is almost exclusively due to the fundamental mode. Then we have our von Mises stress time history, which is always positive. Let's take a look at the command window here. So our peak response is 816.3 G. Relative velocity is about 121 inches per second. The relative displacement about, let's see, 136 thousandths of an inch. The von Mises stress, and then the Hunt maximum global stress due to the stress-velocity relationship. So that von Mises stress and the Hunt value there, those are in the same ballpark, and the fact that they're different by 8% is not really a particular concern to us. So you now have the ability to take a rectangular plate with simply support boundary conditions and subject it to a base input shock pulse. And when I say base input shock pulse, it's actually an arbitrary function, so you could make up your own arbitrary time history. It could be a sine function, it could be a damp sine, it could be a white noise, it could be beat frequency, whatever. Just bring whatever you have and enter it in to this script. Be that as it may, the intention of this is to be used for a shock input. But those others will work as well too. And sometimes we like to do our analyses in the time domain anyway, just for so there's flexibility there, and the idea is to just help you have some tools for, the more tools you have in the toolbox, the better off we are. So I think that does finally finish off our simply supported plate. So these are just the PowerPoint slides for the shock pulse input to the arbitrary plate. Or the shock impulse is an arbitrary input to the simply supported plate. So these plots I've just demonstrated to you, and I'm showing these to you once again just as a reminder, and so you can take a look at what we did. Of course, you can also just download the PowerPoint slides separate from the audiovisual presentation and take as much time as you want going through these. And here are the peak response values summarized. We've seen these values before. Okay, we're going to do this was actually the PSD base input for the same plate. It looks like in the slides I did a switch relative to what I demonstrated in class in terms of order. So we've seen these plots before. These are the simply supported plate, and its responses with respect to the NavMat spec PSD base input. Acceleration PSD, von Mises stress PSD. And then the simply supported plate PSD results. Okay, now we're going to move on to our next boundary condition set. This will be a rectangular plate where the plate is going to be fixed at each corner, so no translation is going to be permitted at each of the four corners. But otherwise, the boundaries are free. This will be an aluminum plate. It'll be bare aluminum, 12 by 8 by 1/8 of an inch thick. And at this point, we're just going to run through and do everything that we did for the simply supported plate for this plate that's just fixed at each corner. Oh, another thing I'm going to mention is with the simply supported plate, we were taking a look at up to 16 modes. Well, for this case where we have this kind of odd boundary condition, we're just going to do our Rayleigh solution. So in other words, we're only going to be looking at the fundamental mode response. If we do need to include higher modes for this boundary condition, then we probably need to switch over to the finite element method, which we're going to do in a couple of webinars, or at some point in this webinar series. So, okay, 12 by 8 by 1/8 of an inch. So let's go ahead and go through that in our Matlab vibration data package. So here we have a fixed point at each corner. And we'll skip over the half-power bandwidth damping method for this boundary condition case, but you can do that at your leisure if you like. So aluminum, and let's see, 12 by 8 by 1/8 of an inch thick. Just make sure I got that correct. Okay, so we're expecting a 76.29 hertz response. And actually, since this is going to be a Rayleigh method, okay, it did turn out to be 76.29 hertz. But if your number is off, by a third or fourth significant digit, don't worry about that, because the way I do the Rayleigh method is I use some random number generation, and depending on the random number seed and all that, your frequency might be different by a fraction of a percent. But anyways, here's that fundamental mode. So you can see that each corner is constrained so that no translation can occur at each corner. Then otherwise, these edges are free, and so you can see what the mode shape looks like. And this is something I've kind of worked on. It may be due for another iteration in terms of improving the mode shape, but I think we're pretty good for a first estimate right now. We're going to apply base input. We're going to take Q is equal to 10. Now, it's going to be uniform for all modes, but there's just one mode. Let's take a look at the transmissibility here. Center of the plate. Let's go 10 to maybe 500 hertz. Calculate. So here's von Mises stress due to the fundamental mode at about 76 hertz. This is the transmissibility, PSI, which is the stress, divided by the base input G versus frequency in hertz. Shear stress is 0 at the center of that plate. Then the bending stress, the SXS and SYY components. So those get fed into the von Mises stress calculation. We have let's get our transmissibilities here. Here's a power transmissibility, G squared out divided by G squared in. And X is equal to 6 inches, Y is equal to 4 inches. That's the center of the plate. Then we have the response acceleration divided by the base acceleration. So this is simply G out divided by G in. And I'm kind of making a mental note to myself that maybe I need to fix that a little bit to make those two y-axes for those two different transmissibility plots a more consistent one with another, but you get the idea. Then the relative velocity frequency response function at the center, and the relative displacement frequency response function also at the center. Now, if you're a motivated student, what you should do next is save the absolute acceleration FRF, or actually you could use one of these others as well, and save that, and then go over to the half-power bandwidth method and estimate the damping and verify that, in fact, it is Q is equal to 10. Let's go ahead and do the navmap base input to this plate, which is point supported at each corner and otherwise free. So we already have navmat underscore spec in our Matlab workspace. Let's look at the center response. And all of our PSDs flash by. So we have our stress PSI squared divided by hertz versus frequency in hertz. That's the von Mises stress. PSD, overall level, 387 PSI RMS. We have a relative displacement PSD, inches squared per hertz versus frequency in hertz. We have a relative velocity PSD, inches per second squared per hertz versus frequency in hertz. We have our acceleration response PSD superimposed on the base input from the navmat. So that's G squared per hertz versus frequency in hertz. So we get those set of PSD functions. We can save them if we like. And then here we just have a summary in our Matlab command window of those response metrics in terms of their respective overall RMS levels. Okay, I'm just going to close all and close out of those plots. And the other thing we're going to do here is we're going to put in that shock, our synthesized shock time history. That's an arbitrary pulse. So our input array here is SRS 1000G underscore SRS. Let's look at the center of the plate response. Okay, and I note that I have an error. Okay, typo on my part, excuse me. That file did not exist. I need to get the name right. It's SRS 1000G underscore Excel. So, typo error now corrected. And we have all of our response time histories appear. Let's just, I'm going to ignore the SXS and SYY plots. Here's our von Mises stress time history, PSI versus time in seconds at the center of that plate. We have our response acceleration at the center. You can see the effect of the higher modes there at the onset of the response. Here's our base input. We've seen that before. a couple times. Oops. Base input acceleration. We have our response acceleration, our relative velocity, inches per second, versus time in seconds. So as we get to relative velocity, you can see there's still a little bit effect of the high frequency modes, but mostly it's that mode at 76 Hertz responding. And then as we go to relative displacement, you can see the 76 Hertz fundamental mode clearly dominates the response. Now if we go to our peak response values here, so you can see our peak response acceleration is 181.8 Gs, and that was our plot as shown in that figure. So the peak is 181.8 Gs. Relative velocity, 106 inches per second. Now, if you remember that mil standard 810E rule of thumb, for military equipment, the shock severity threshold is 100 inches per second. Well, this is bare aluminum, and bare aluminum has a shock severity of about 400 inches per second, which is about 12 dB higher than the mil standard threshold. Well, the mil standard threshold is for military equipment, whatever that might be. But bare aluminum by itself has a higher threshold. So we're still well within the yield limit for aluminum. Then we have our relative displacement and our von Mises stress. Now, in terms of the stress-velocity relationship for plates supported for rectangular plates, points supported at each corner, I'm kind of still playing around with the formula. But what I've kind of found from some numerical experimentation is that the stress velocity is roughly about 2 times rho times c. Actually, this lower limit here I have set to about 1.9 times rho c times velocity, and the upper limit is about 2.5 times rho c. And so in this case, each of the two stress-velocity relationships are higher than what the von Mises stress gave us. So I may need to do a little bit of work there, but it's still kind of in the same ballpark, with the stress-velocity relationship more conservative in this case. But if I were doing this analysis, this value here is what I would use. I would take the von Mises stress. Although to be more thorough, we should probably go back and maybe have another synthesized shock pulse as well, and see how von Mises stress varies as we vary the input time history, where each of those time histories would be satisfying the same shock response spectrum specification. Okay, so I've done quite a bit of talking here, and I want to close out the plots now. Okay, let's go to, so if we go back to the PowerPoint slides, you'll just see, okay, there's our fundamental bending mode for a plate supported or fixed at each corner. We entered in a Q value of 10. We took a look at the acceleration transmissibility at the center, the von Mises stress at the center. Then we did our shock analysis where we applied that base input. So you see the response acceleration, G's versus time in seconds at the center. Peak response values summarized there for the shock response. And then we applied the NavMat base input to our plate fixed at each corner and took a look at the response at the center. So for the NavMat input, if we take the square root of the area under the response curve, that equals 9.78 GRMS for that response. And again, this being a PSD, it's G squared per Hertz versus frequency in Hertz. Then the von Mises stress PSD, 387 PSI RMS. And then just a summary of the output metrics in terms of their respective overall RMS values. Okay, and that concludes our webinar unit for today. And I hope you've enjoyed this and hope you can use these tools for your actual work, your research. And we're going to be continuing on with rectangular plates and circular plates and annular plates in the upcoming webinars. So have a good day, and thank you, and goodbye for now.